Hello, a great welcome to this series on earthquake resistant design of structures explained through the caudal portions contained in ASCE SEI 722. So we are making a lot of progress. So today we are at topic number 6. So here we'll address in detail the very important seismic design parameters, response modification coefficient capital R, overstrength factor omega, and deflection amplification factor CD. So let us get into the details. So before explaining the response modification capital R, I would like to say that the basic seismic analysis procedure adopted in ASCE 722, it uses a response spectra, and we know that this spectra is representative of the ground motions expected at the site, but it is substantially reduced. And here comes the relevance of response modification coefficient capital R. Accordingly, remember that the structural elements are expected to yield, buckle, or otherwise behave inelastically when it is subjected to the actual ground excitation represented through the risk targeted maximum considered earthquake MCER. Now to explain the response modification coefficient capital R, let me take you to a standard lateral force drift plot prepared for a moment frame that is shown here. And this is directly taken from the commentary section of ASCE 722 and slightly modified. And here also I have added some indicative diagrams in order to get a better clarity on what this plot represents. And if you look into the figure, you can say that along the x-axis, we have the lateral drift represented through delta, and along the y-axis, we have the lateral seismic force V. Or in other words, the plot that is shown in this diagram is a relationship between the lateral drift delta and the seismic force V, which is prepared for a moment resisting frame as shown here. So in order to capture the real picture of or the real meaning of the term response modification coefficient, I would like to take you through some important terms. The first one is, as you can see that here there is a term called VE. And first of all, let me explain you what is VE. VE represents the maximum lateral force that is generated in a structure if elastic when subjected to design ground motion. Obviously, we know that the design ground motion is nothing but 2/3 of the MCER. That means if the structure is allowed to remain elastic under an seismic excitation equal to 2/3 of MCER, it develops a maximum lateral force VE. Now in the same diagram, you will find that there is a term called Vs, which is nothing but the design lateral force that is computed following the code specified response spectrum. So first observation that we have is the design force level that is mentioned in the code is much less than VE, which is nothing but the maximum force generated in the structure if it is allowed to remain elastic during the seismic excitation. Now, in order to get a better clarity on R, let us rewrite the equation for R as, now how do we define R? First of all, R is defined as VE by Vs. VE by Vs. Remember, V is the maximum force generated in the structure if it is elastic. That is very important. And Vs is the code specified design lateral force. Now we can write this expression R equal to VE by Vs as the product of two distinct terms. The first one is VE by Vy, and the second term is Vy by Vs. We have covered the terms VE. We also covered the term VS. Now there is one more term known as VY. Now let us explain VY. What is VY? Now again, going back to this diagram, we know that Vs is the design force level at which the structure is designed to remain elastic. Now, as the lateral force is gradually increased, we will find that at some force level, V, which is higher than Vs, the first hinge develops in the structure as shown here. So here is a frame, that is a moment restricting frame. You will find that the drift is marked delta here, and V is the seismic force. So we find that at a lateral force level V, which is higher than Vs, the first hinge, that is we call it as the first significant yield of the structure, happens as is shown here in the yellow circle. Now when the lateral force V is gradually increased, the first thing is that we find that the yielding gradually spreads, as is indicated in many yellow circles, to some other locations of the structure. But unfortunately, the structure develops the resistance at a much slower rate. Now, on further increasing the lateral force level, we find that at a particular level of the lateral force V, which is equal to Vy, we find that sufficient number of plastic hinges has formed in the structure to reach its fully yielded strength Vy, so that any further increase in the lateral resistance V is not possible. So how do we define Vy? Vy is nothing but it is defined as the fully yielded strength, or in other words, we can interpret Vy as the maximum lateral force generated in the structure if it is inelastic when subjected to the design ground motion. So remember, the difference between VEE and Vy is very clear to us now. VE is the maximum force generated if the structure is elastic, and Vy is the maximum force generated in the structure if it is inelastic. Or in other words, we can say that the drop in the seismic demand from VE to Vy is just because we allowed the structure to remain inelastic. So that is the relevance of the term VE by Vy. So there is a drop in the demand from VE to Vy. It's all because we allowed the structure to remain inelastic, and accordingly we often denote VE by Vy as RD, and this RD is nothing but it is known as the ductility reduction factor, or in other words, it's a reduction in the seismic demand which happened because of the inherent ductility of the structure. Now let us talk about Vy by Vs. So now it is very clear to us that the code specified design level is Vs, whereas the structure has reached a fully yielded strength of Vy, and we know that Vy is higher than Vs. So let us go back to this diagram. So Vs is the design force level for which we designed the structure to remain elastic, and we find that the structure fortunately has a fully yielded strength, or is a full resistance Vy, which is much higher than the design specified force level, and this is simply because of the overstrength of the various components present in the lateral force resisting system, and accordingly we call this as Vy by Vs, that is represented through a term omega, where omega is known as the overstrength factor. Or simply we can find that the total reduction represented through the response modification coefficient R, it basically comes from two factors, one represented through RD, which indicates that this reduction in the demand is due to the inherent ductility in the system, and there is one more important factor contributing the reduction in the demand, which is nothing but the overstrength factor. So thus, the total response modification coefficient capital R is RD into omega. And here I have defined all the terms VE, VS, VY, RD, and omega. And thus, to conclude this page on R, we can say that the intent of R is to reduce the seismic demand. How did we reduce the seismic demand? We have accounted for the displacement ductility demand required by the system and also the inherent overstrength omega of the SFRS. And considering these two factors, accounting for the ductility and the overstrength, we have reduced the seismic demand from VE to a code specified level of VS. That's all regarding the important concept behind the formulation of the response modification coefficient capital R. Now let me take you a little bit more on to the overstrength factor omega. Now this is the same figure which I have reproduced in a better simplified format. It's the same drift versus the force level, and referring to this, we find that Vs is nothing but it's a code specified design force computed using the response spectra, and Vy is the fully yielded strength, or it is nothing but the maximum resistance or the maximum lateral force generated in the structure if it is allowed to remain inelastic. Thus, the overstrength factor omega is nothing but Vy by Vs. Now you may ask where this overstrength comes from. And basically this overstrength, it comes from two sources. The first one, it comes from the overstrength of the components, beams, columns, braces, etc. that forms the seismic force resisting systems. And second one, or maybe this contribution is less compared to the overstrength of the material components. And the second component is the distribution of the lateral force that is used for obtaining the capacity of the structure. So please remember that the values of R and the values of the overstrength factor omega are provided for different seismic force resistance systems in table 12.21 of the code. Now let us discuss what contributes to the system overstrength. So remember that the overstrength factor, which is basically defined as a Vy by Vs, sometimes you'll find that this could be the Vy in many cases could be even 30 to 100% higher than the design seismic force Vs. Now you may be wondering, what is contributing to this much of a hike of a Vy compared to Vs? The first one is the actual material strengths. We know that the actual material strengths are always higher than the nominal material strength specified in the code. For example, let us talk about a reinforced cement concrete structure. And we start with two materials. First one is the concrete and the second one is the reinforcement steel. When I say that the design strength of the concrete cylinder is 28 MPa, rather than 28, the actual strength could be 33. And again, similarly, when we talk about the reinforcement steel, we say that the yield strength of the steel is 415. So if you actually measure it, instead of 415, it could be 440. Thus, we find that the actual material strength specified in the code are always higher than that is the nominal strength specified in the code are always higher than the actual material strength. And what is the second factor that is contributing to the material overstrength? The member design strengths usually incorporate a strength reduction factor to produce a low probability of failure. For example, if you refer to the ASCE, you will find that there is always a strength reduction factor, whether you are designing the member for fracture or the shear. And this strength reduction factor also contributes to the material overstrength. And now coming to the third one, the designers can introduce additional strength by specifying reinforcement patterns that exceed those required by the calculations. Similar situations occur where the prescriptive minimums of the standards control the design. So this is very simple. For example, when we talk about the reinforcement patterns that exceed the that required by the calculations, for example, suppose that we designed a column, we arrived at 13 numbers of 20 die bars. Instead of 13, obviously, we will go for 60 numbers, which means that this reinforcement pattern of a 16, it is much higher than that calculated by that obtained by the calculations, that is 1320. So this will again introduce some material overstrength. And then there are many situations during our designs that the prescriptive minimums of the standard that control the design. For example, maybe that we have designed a beam and we ended up in a reinforcement which is much lower than the minimum prescribed by the standard. In such cases, we provide a reinforcement which is equal to the minimum, and this minimum is much higher than that is required by the structure calculations. And this again is another scenario which contributes to the material overstrength. Then finally, we know that the design of many flexible structural systems, for example, whenever you go for the design of a moment resisting frame, you will find that in many cases, it is not the strength, but it is the stiffness or it is the drift that govern the design. In which cases, we may have to increase the section dimensions to control the lateral deformations rather than to provide the specified strength. And this is another factor that contributes the material overstrength. Thus, we find that there are many factors inherent in any structural system that contribute to the material overstrength. And this material overstrength, please remember that it is always higher than 30 to 100%. And this material overstrength results in a fully yielded strength of the structure which is 30 to 100% than the design seismic force level Vs of the code. Okay, fine. Now let me take you to another factor, that is the deflection amplification factor CD. Now remember that the code specifies a design force level that is indicated by the Vs. And at this force level Vs, obviously we know that the structure remains elastic, and this will provide a corresponding drift, that is a delta D. And now the deflection amplification factor is defined as a CD, that is equal to delta D by delta small d. And remember that delta capital D indicates the drift, the actual drift that results from the design earthquake ground motion. Now let me take you to this diagram, again back to this diagram. Yes, so look here, we know that Vs is the code specified design force level, and correspond at Vs we know that the structure is elastic and the corresponding deformation is delta D, delta subscript small d. Now we need to multiply delta D, we need to multiply delta small d by a coefficient which is known as CD, in order to calculate the design drift of the structure when subjected to the design level seismic motions. So remember that the design drift delta capital D is always in the inelastic segment of this load versus drift curve. So what does this mean? This means that if we want to compute the inelastic drift, of the structure under the design ground motion, that is 2/3 of MCER, what we need to do is we straightaway compute the drift of the structure at the code specified level, that is Vs, multiply this deformation delta subscript small d by the deflection amplification factor CD in order to compute the inelastic drift that is actually experienced by the structure in the event of the seismic ground motion that is 2/3 of MCER. So remember here, CD is defined as delta subscript capital D divided by delta subscript small d, where, as already explained, delta small d indicates the elastic drift computed at code specified design force. Remember, delta D is elastic and delta capital D is nothing but inelastic drift resulting from the design earthquake ground motion. Now, the values of this deflection amplification factor CD is provided again in a table 12.21 of the code, and in many cases it is found that the value of a CD, it is found to be less than R. And you may ask, where do we use these amplified deformations, or where do we use the inelastic drift? This inelastic drift, which is the actual drift undergone by the structure in case of the design ground motions, these amplified deformations are used to assess the story drift. So remember, while calculating the story drift, we have to include the inelastic drift into account by multiplying the elastic drift by the coefficient CD. And these amplified deformations are also used to determine the seismic demands on elements of the structure that are not part of SFRS, and also on the forces developed in non-structural components within structure. Okay, fine. That's all our discussion on the three important seismic design parameters, namely the response reduction coefficient, capital R, then the overstrength omega, as well as the deflection modification factor CD. So if you have any kind of queries, so please let me know through the comment box. And as usual, don't forget to subscribe the channel by clicking the right button in the corner of the screen. So that's all. Thanks a lot. Have a nice day.